Hello, hello, and welcome to the stream. Of course, this isn't actually a stream because the privacy is set to unlisted. I have my reasons for that, and the reasons are as follows. One, I am incredibly neurotic. I don't like to be perceived in real time because then I start stalling. It's known as the stalling problem in Josiah theory. Check out the Josiah Theory channel, by the way. Be sure to subscribe. You know, we're going to be moving this kind of content over there soon. But, yes, in Josiah Theory, the stalling problem has been long unsolved. So we're going to try and circumvent that today, the so-called easy route. And we're just going to leave this unlisted and we'll publish it when it's done. Now, for the stream today, we are going to be exploring binary strings. So let's go ahead and, well, first of all, let me get a different, I have a laptop under here, as you can see. I'm experimenting with setups, and I don't really like this one. So what I'm going to do is I'm going to move that laptop aside and put this down. There we go. Isn't that nice? Okay, so now that I have this down right here, I'm already starting to be very self-conscious. I'm noticing that I'm doing like a presenter voice, right? Like I'm doing a presentation. I'm making my voice a little deeper. I don't talk like this normally. Normally I talk like this. So I guess I should just speak like myself. So good. We've already decided to start speaking like ourselves, which is really good for us as a community. I'm very insecure about the way I sound, but that's okay. That's okay. Oh, let's see. The stream's current bit rate, 2600 kilobits per second. It's lower than the recommended 4500. Fascinating. So apparently I can change that. Let's see what the stream settings say here. Maximum video bit rate, video, audio, output, video bit rate. Ooh, let's try 4500 then. Okay, apply. Okay, so I've changed that setting. I'm not sure if it's actually going to work, but worth a shot. Okay, so hello, my dear viewer. So here we are. You know, we've got our notebook here. And that's great, right? It's good to have. Oop, I dragged the video there. So we've been live for 3 minutes now, haven't even gotten to the good stuff. So now I feel like I can actually write comfortably. So what are we working with? Binary strings. So what are binary strings? Binary strings. String is just a bunch of stuff connected, a bunch of symbols connected to end to end, right? So like these words, binary strings, this itself is a string, although it's not a binary string. Binary string is when you connect a bunch of symbols end to end, and those symbols are either 1 or 0. Okay. So an example of a binary string would be, well, a binary number. 1 0 1 1. There you go. So here's a binary string. 1 0 1 1 0 0 1 0 1 1. All right. And as a binary number, you may know that that is, what would that be? That's 1 plus 2 plus 8, 11, 64, 55, 75, 75 plus 128 plus 512, which would be, let's do that. This is very important. 75 plus 128 plus 512, which would, of course, be 715. So that's what that would represent as a binary number. You have to take note of things like this. So this is, right. But we're not actually, we don't really care about the number part, you know. We're not really looking at these in order to do arithmetic with them. like addition, subtraction, etc. We're just kind of looking at them as little strings of numbers, characters, symbols, more generally. Great. So we figured out what binary strings are. Okay. So, let's establish some attributes of the binary string. So what's in a binary string? Let's write that. What's in a binary string? You have its length, first of all. Now, if we were talking about just like what's in a string, first we would say it's alphabet. The alphabet is all the different kinds of symbols that will be joined together end to end. But by saying binary, we're already saying what the alphabet is. We don't want to look at too many different possibilities. You'll find very quickly that that's what we're interested in here. We're interested in possibilities. So, the length. So what's the length of this string? Just count the symbols. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here. It's 10. So we would say n equals 10. For this binary string. Okay, great. So what are some other characteristics we're interested in? We're interested in the number of ones that are in the string. You may already be asking, why are we interested in this? But that's the thing. We get to decide what we're interested in, because that's how math works. There are no rules. So we're interested in the number of ones in the string. There are different names for this count. In this case, the number of ones are, 1, 2, 3, 4, 5, 6. There are 6 ones, okay? There are different names for this. You could call it the number of ones, Other words are the population, as well as the Hamming weight. And I rather like the term Hamming weight. It's got a certain oomph to it, so we're going with Hamming weight. Number of ones. Okay. And so in a more general string, the one that isn't just binary, we would say that the Hamming weight is the number of characters which are non-zero. Anyways, I need to stop talking about things that aren't binary, because that's just going to convolute this video, and if I'm going to keep talking about them, then I might as well have talked about them to begin with. So here we go. The Hamming weight, that is to say the number of ones. We say D, also the density. That's why I'm choosing D. You could also call it the density. Nevertheless, we'll call it the Hamming weight, and we'll use the symbol D. Make things as confusing and inconsistent as possible. And we'll say that D here is 1, 2, 3, 4, 5, 6. So D equals 6. So this is a binary string where n equals 10 and D equals 6. Okay, so let's stop here for a moment. Let's just kind of, take it all in. I want to share some of this relaxing thunderstorm sound with you guys, so I'm going to bring that in. Okay. Helps me focus, helps the nerves. So just a recap. Binary strings. Okay. Length, n equals 10. That's the number of bits, digits, symbols in the string, whatever you want to call them. And then the Hamming weight, or density. It's the number of ones in the binary string. And that is 6, so we say D equals 6. Now, of course, this is not the only binary string with the attribute of n equals 10 and the attribute of D equals 6. There's a whole class of binary strings with these two attributes. So let's get this out of the way real quick. We want to count things. So why do we want to count things? And what do I mean by that? So the useful thing about counting is that you can figure out the full swath of what's possible with a certain kind of mathematical object. Now, this is a certain kind of mathematical object we're looking at here. Binary strings with a length of 10 and a Hamming weight of 6. There is only a certain specific number of that kind of mathematical object. And you can count that, right? Why would you do that? It's useful, and we'll take it's useful as an axiom for the rest of our studies. So whatever we're looking at is useful and has world-saving applications. So now we don't have to think about that anymore. Great. So we want to count things. It's important. More specifically, we want to count possibilities. Think of it that way. In which case, math is a game where we play God. And we say, okay, what's everything that's ever been possible, right? You can count the number of possibilities, but counting is just the beginning. Because then you can actually generate a whole list of possibilities, a whole set of possibilities, if you will. You can enumerate them in various ways. You can relate all of the possibilities through various schemes. You can draw different graphs of their relations. And in doing this, you figure out everything. And that's what we want to do because that gets us off. So we want to count things. Let's get an example for that. We'll write example. Okay. We'll ask a question here. How many 1-bit binary numbers are there? Now, this is an interesting question. Another way of phrasing the question. How many binary strings length n are there? We'll just write here. Same question. Now, I want you to notice that although these are different words, different labels, they describe the same thing. So, for example, 1 bit. I forgot to write, I'm sorry. That's too general of a question. Length n equals 1. So 1 bit and n equals 1 are describing the same thing based on how I defined n over here. Let's draw a little arrow to that. Not the nicest arrow, but we'll work on that. You know, maybe if we fan it out a little right there. Sorry about the arrow, guys. Okay, great. So those are the same. Binary numbers, binary strings. And the question of how many as well as the syntax of the question mark. Let's go ahead and include length in that. So this should highlight the isomorphism between these questions. How many length n equals 1 binary strings, question mark. How many 1-bit binary numbers? It's the same question, hence the question mark, as well as the parallelism between the content. Now, you can look at it, of course, like a graph, but we're not going to go there yet because I wanted to keep this introduction nice and simple. Okay. So, now that we've asked these questions, we can continue. So, think about it. In a binary string, you have an alphabet. What's the alphabet of a binary string? It is 0 and 1. Now there's like a special symbol you can use. I don't really know it, but I'm gonna pretend it's this. We'll say that's the alphabet of a binary string. 0 and 1. Okay? So, 2 possibilities per bit. We'll just use the word bit to refer to a given position in a binary string. Okay? So, if there's only 1 bit, and there are only 2 possible symbols, the answer, 2. The answer is 2, for the reasons I've just laid out. So, we can turn this question into a shorthand sort of function form. And the way we'll do that is we'll call this B of n. And so, B of, apologies, B of 2, sorry, B of 1 equals 2. let me list out the two different binary numbers. Binary strings, rather, of length n equals 1 that you can have. 0 and 1. So let's just reflect on that for a moment. Now, this, with the lowercase b, indicates that we have a count, a quantity. This is a counting function. But maybe we want a function whereas this will return a number of something. Maybe we want a function that will return the set of things that we're counting, the set being counted. Let's give this a different form. Instead of being stacked that way, vertically, let's write it in set notation with the curly braces. Okay? And we'll call this B, capital B of apologies, 1. Okay. And you may notice something here, which is that it is equivalent to the alphabet itself. So the swath of possibilities, when there's only one character in the string, is always going to be equivalent to that string's alphabet. Okay. But then we continue. And we say, well, what about n equals 2? So what would be b of 2? So let's count. Now we're talking about 2-digit binary numbers. So what's the first one? Well, we'll start with our first character twice. 0, 0. There's our first one. Then, let's increment that rightmost character, as if we're counting upwards in binary. 0, 1. So then, let's reset that to a 0 and increment the left digit. 1, 0. And then finally, 1, 1. So here we have every 2-digit binary number you can form. Every binary string of length n equals 2 that you can form. The count of which is 1, 2, 3, 4. 4. Okay. So b of 1 gave us 2, b of 2 gave us 4. Let's keep going. N equals 3. Let's see. B of 3. 0, 0. Sorry. We're going to have a third 0 this time. 0, 0, 0. 0, 0, 1. 0, 1, 0. 0, 1, 1. 1, 0, 0. 1, 0, 1. 1, 1, 0. And finally, 1, 1, 1. You may be noticing something here because now we have 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 total binary strings of length 3. Just as there were 4 binary strings of length 2 and 2 binary strings of length 1. You may be noticing a pattern is that they are doubling. Now we're not going to keep going with this. I think I've made my point. That it doubles each time. So now we can do the math and we can generalize this. We're going to say that the function b of n, now we're putting our letter in there, our symbol that represents an arbitrary length. B of n is equal to because there are 2 possibilities, and when there's 1 place, there's 2. 2 places, there's 4. 3 places, there's 8. The answer here is that b of n is 2 to the n. 2 to the nth power. So 2 to the 3 is 8. 2 to the 2 is 4. And that makes sense, because it's doubling each time. And all 2 to the n really means is that we're multiplying by 2 an extra time each time, which means that we're doubling an extra time each time. So all this is saying is we're doubling n amount of times. Just as if this were 3 to the n, that would mean we're tripling n amount of times. Right. Okay. So great. We've figured out now a very solid starting point at which we now know that there's always going to be 2 to the n binary strings of length n. Okay, so let's write that down. There will always be 2 to the n binary strings of length n. And you know, there's something exciting about that, to me at least. The excitement perhaps comes in the form of, you know, it's that entire swath of possibilities. Now, you should appreciate the fact that this is exhaustive. I mean, there are no edge cases to be accounted for here, and no unexpected possibilities that we haven't accounted for. These are the only two-digit binary numbers that there are. These are the only 3-digit binary numbers there are. There will always be exactly 8 3-digit binary numbers, exactly 4 two-digit binary numbers. And that's a beautiful thing. I mean, it really is. Really is. So, I mean, just kind of sit on that for a second, because it's, well, damn, I mean, it's a beautiful thing, right? It's a beautiful thing. So we move on, okay? So, let's look at the 1-digit binary numbers again, okay? 0 and 1. So let's add in our second attribute, right? Hamming weight. Okay. So of these two, what is the maximum Hamming weight of an n-digit binary number? Let's figure that out first, okay? And let's start with a 1-digit binary number. Okay. I think this is a good question. So let's investigate it. What is the maximum Hamming weight of a 1-digit binary number? In which case, we're basically just asking, how many ones can we possibly have in a 1-digit binary number? Now, to the more bright and keen and sharp of you watching, you may note that the answer to this is 1, because you can only have a single 1 digit. That is to say, a digit of 1, right? There's only one space to have that. The answer is 1. We'll say max HW means Hamming weight for 2 digits. And for this, well, we can look at every 2-digit binary number and we'll see what's the most ones that we see. Oh, 2 ones. So, 2. 3 digits. Let's see. I'm seeing Hamming weight of 1 here. Oh, a Hamming weight of 2. A Hamming weight of 3. 3. And I think maybe my intuition is telling me that we can generalize this to say the max Hamming weight of an n-digit binary number. And apologies for switching over to the n-digit binary number lingo instead of saying binary strings of length n equals blank. But as I've said over here, these are the same thing. Totally isomorphic. That's what we say in math. We say isomorphic. So don't worry about it. You know, you use the terminology. It's context specific, right? You use the terminology that works in the context. And the context is always changing, so you gotta, it's like you gotta keep up with it, right? So, the max Hamming weight of an n-digit binary number is n. Just n. That's it. So the max Hamming weight is the length of the string itself. Okay. So, let's look back at this again. Let's look back at our 3-digit binary numbers. I'm going to write them like this. And we are going to write them in a different order now. See if you can pick up which order I'm writing them in. Okay. We'll just go with that, I guess. Kind of sloppy, but given a vertical representation here. Guess we should make sure there are commas here, so they're separated. Okay. So, I've given them a different order here to highlight something here. What I'm highlighting is that you can group these possibilities. You know, these are all the different 3-digit binary numbers that you can make. You can group these possibilities based on Hamming weight. So D equals 3. This is the one 3-digit binary number with D equals, oh, excuse me. My apologies. With D equals 3. And then right here you have the D equals 2, 1, 2, 3 of them. D equals 2. And right here you have the 1, 2, 3. Oh, okay. D equals 1. Then finally, D equals 0. Okay. Just as for these two, we have D equals 0 and D equals 1. And we'll give a little count next to them too. So there's 1, D equals 0, and 1, D equals 1. How many? Let's get a little separating line here. We'll say there's 1 binary string of length 3 with a Hamming weight of 0. There are 3 binary strings of length 3 with a Hamming weight of 1. There are 3 binary strings of length 3 with a Hamming weight of 2. And 1 binary string of length 3 with a Hamming weight of 3. Okay? So, now that we've done this, you may notice something. Okay? Kind of soak it all in. And I really want to emphasize the space. You may have been noticing, like, how slow and how we're really... Oh, apologies for the shaking. How we're really trying to take our time with this. You may ask, why is that? You know, you might be used to, like, boom, 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 you know, like a real machine gun pace that you see a lot on these video services, and I'm against that. I don't really like that. I think that it's time to slow down. We're going to start slowing down now. So, what we're going to do here is notice something. Look at these numbers. You can add them together. 1 plus 3 plus 3 plus 1 equals 8. And the number of 3-digit binary numbers is 8. So, these Hamming weight groupings can be said to partition the number of binary numbers of this given length, which is 3. Okay. Now, there's some way that you could formalize this and write it out. And let's take a pause here to meditate on this. Always do this. When you don't know something, don't speak. No. Don't speak. That means it's time to sit and think. So we're going to sit and think. Nature's genius arrives at its own pace. It's not our genius. Never think that it's your genius. It's nature's genius. So we say the binary strings of length n The binary strings of length n are partitioned by the binary strings of length n and Hamming weight d. Now, I'm not a huge fan of this wording, and here's why. It's kind of redundant in the way that I say the binary strings of length n twice. But in lieu of a more, efficient naming scheme, this is what we're going with. Because it's true. These are not just the binary strings of length n and Hamming weight d, but also just the binary strings of length n. I mean, if you cover up this side, you just get the binary strings of length n. But then, if you show this, you see the grouping into the various sizes of d. Okay? Something which hasn't been explicitly said, but I think is worth addressing right now, is that the Hamming weight of a string is a non-negative integer. Okay. That is to say that you cannot have a negative Hamming weight. It doesn't make sense. Because you are counting something, right? The lowest you can go is 0. The highest you can go is the length of the string itself. Just for completeness sake, for the examples we've given, length 1 through 3, let's look at length 2 real quick. Okay, we'll use the same format. 0, 0, 0, 1, 1, 0, 1, 1. Okay. I'm going to omit the curly braces. They're a little bit fucky. So once more. 0. At our line again. Adding some labels, make things easier to read. Okay. Oop, made an oopsie. We had a scribble here to make sure that the viewer knows that we did not mean to write that. So these are the 2-bit binary numbers of Hamming weight 1. And here is the 2-bit binary number of Hamming weight 2. This here. The counts of which are 1, 2, and 1, and just as 4, let's, for completeness, 2, 1 equals 2, and 4, of course you get b of 2 equals 4. Well, there you go. So, just as I said, the binary strings of length n, in this case 2, so binary strings of length 2, are partitioned by the binary strings of length 2 and Hamming weight d. Well, and let's say d equals 0 through n. Okay? And that is true. So what does it mean for something to be partitioned? Perhaps we should define that real quick. For a number to be partitioned is to just separate the number into what we call addends, which are just numbers that you add together. So here's 4, and we can ask a question then. How many ways can 4 be partitioned? And for now, we'll just call that P of 4. Well, first of all, 4 by itself, 4 plus nothing is 4. But then there's also 3 plus 1. Okay? Then there's also 2 plus 2. There's also 2 plus 1 plus 1. And then finally, there's 1 plus 1 plus 1 plus 1. And you'll find that the partitions of 4, a subset of this set that we've found, a subset of these are the divisions of 4. So a division is really just when you partition an integer into the same number. So 4 here is the same as 4 divided by 1. 2 plus 2 here is the same as 4 divided by 2. 1 plus 1 plus 1 plus 1 here is the same as 4 divided by 4. So 4 divided by 1, 2, 3, 4, when all of the numbers are the same, is that number itself. 4 divided by two different numbers, when those two numbers are the same, is that number itself. 4 divided by 4 is 2. 4 divided by one number, when that number is the same as itself, which is always going to be one number, as you may be able to intuit, but be careful of your intuition. 4 divided by 1 is that number itself, which is 4. Okay, so that's an interesting, discrete sort of way of thinking about division. As being a subset of partitions. A particular way of looking at the subset of partitions. It's fascinating. Very fascinating. So, now, it's time to take a potty break. And I'll be right back. Thank you for bearing with me. So, I'm going to be taking a bulk laxative now. It's called Citracel. It's similar to Metamucil. It is methyl cellulose fiber. Methyl cellulose fiber therapy for irregularity. Great taste. I'm going to be dropping that in my water glass here. See if I can get this. Looks like there's a little hair in there. There we go. Okay. To put a scoop and a half in there for the days when I'm really blocked up. We just mix that in there. Nice and mixed up. I imagine this stuff is essentially sawdust, but orange flavored. So that's pretty nice. Okay. Very nice. And, well, you don't want it to settle, so you drink it as quick as possible. Ah, delicious. Very nice. Very nice. Very nice indeed. Okay. So, where are we now? Let's take a little recap. It's always good to take little recaps. Now we're almost an hour into the stream. I guess I should say recording. So, now that we've come this far, first we introduce binary strings. All the technical stuff aside, it's a binary number. It's a 2-bit... No. It's a number with 2 possible values per bit. Per digit, if you will. Okay. Alright. And so, you'll see here that we introduce the concept of length, that is, how many digits are in the number. And we introduce the concept of Hamming weight, or density, which is the number of ones in the number. Or string, whatever you want to call it. It's context specific. You know, sometimes it makes more sense to call them strings, because number kind of implies that you're going to be doing arithmetic, right? You're going to be adding, subtracting. Like, oh, I'm going to add 0, 1 to 1, 0, and that will get me 1, 1, you know. But even though over here I'm not really doing arithmetic with them, I'm still referring to them as binary numbers purely out of habit. It feels more natural to me. And at the end of the day, it's a good thing to do. Just use whatever nomenclature is more natural to you. There's, of course, the problem with consistency and confusing people, but never mind that. So, we introduced Hamming weight. We established that we want to count things. The name for this, by the way, concerning with oneself with counting and enumeration and whatnot of possibilities, is combinatorics. Okay, so then we asked questions. How many 1-bit binary numbers are there? How many 2-bit binary numbers, etc.? And we finally found out that there are 2 to the n-bit binary numbers. Okay, so there are 2 to the 2-bit binary numbers. You know, how many 3-bit binary numbers are there? 2 to the 3. 8. Okay. So then we move on, and we looked at the Hamming weight. Okay? Now, this is where it gets interesting. Because we can ask another question. How do we count n-bit binary numbers where Hamming weight equals some number d, right? So like we have a count here. So for 3-bit binary numbers, how many of them have a Hamming weight of 1, of d equals 1? And the answer to that is 3. But just as we have a formula for that over here, how do we derive that formula over here? There's an answer to this. Okay. You may hear me Googling on the side here because I'm pulling the answer up. The answer is, binomial coefficients. Okay. So, what are the binomial coefficients? What's that? You may be asking. It's all the ways you can choose k objects from a set of n. Or n choose k. We say n choose k. Right? So this sounds kind of abstract. I'm talking about letters like k and n choose k. So an example. To get this number 3, we were asking the question, 3 out of 3 digits, choose 2, right? So like maybe you could look at it like, these are all the different ways that you could choose 2 out of 3 of the digits, right? You could choose the first and second digit, you could choose the first and third digit, or you can choose the second and third digit. All right? And the count of those possibilities is 3. So the way we write this is like this. And choose k. All right? So, in our example up here, 3 choose 2, is 3. So you may be asking a question now. And that question is, well, what's the formula then? Surely there's a formula. And there is. There is a formula. I'm going to give it to you now. But before I do, we need to go over something first. We're going to go over an operator. Factorial. The exclamation mark, as I write here, is the factorial operator. This is very important in combinatorics. Okay? So what is factorial? Okay. So factorial, I'm gonna Google real quick to make sure I get this right. Okay. So it works on a non-negative integer. So the lowest number that you can factorial is 0. Okay? So n factorial n factorial is the product of all positive integers less than or equal to n. So just as an example, 4 factorial, what do you think that would be then? The product of all positive integers, so we're not looking at like -1, -2, any of that. No. The product of all positive integers less than or equal to n. Okay? That means that, well, less than or equal to n. We would start at n, so 4, and then we just go down. Times 3, times 2, times 1. And we stop there because we're looking at the positive integers, and 0 is not a positive integer. Otherwise, whatever we got here, once we multiply it by 0, it would just be 0. And of course, you could do it the other way around too. You could start at 1 and then do 1 times 2, 2 times 3, etc. In fact, that may be more intuitive, but regardless, we get the same answer. What's the answer? 4 times 3 is 12. 12 times 2 is 24. And anything times 1 is going to be itself, so 24. So 4 factorial is 24. So that's it. Now, it may be more intuitive to look at it the other way around, especially when you consider that. Let's look at it like this. 4 factorial is also 3 factorial times 4. Interesting, right? Just as 3 factorial is equal to 2 factorial times 3. You can say that n factorial is equal to n minus 1 factorial times n. So what's the point of that, right? Well, people who ask questions like that, well, I'll just give you the answer. That's interesting because this is known as the recurrence relation. Right? But we don't need to think about that right now. All we need to know is that this is what a factorial is. That's our little blurb, our little info blurb that we've learned. So now we can finally move on to defining our formula for combinations. N choose K. Choose K L L. Combinations, that's what this is called. N choose K. How many ways can you choose K elements from a set of N? Alright, and let's finally write our formula. Here it comes. It is N factorial over K factorial times n minus k factorial. Now, isn't that something, isn't it? Isn't that something? I do think it is. So there we have it. So, let's reflect on this for a second. Let's just kind of aimlessly peruse the landscape that we've created here. It's quite the landscape. It's quite the landscape. So, going back to this, there are 2 to the n different n-bit binary numbers. And we can say that, let's do this over here. And there are n choose d n-bit binary numbers of Hamming weight d. So just as we established earlier that the binary strings of length n are partitioned by the binary strings of length n and Hamming weight d equals 0 to n, we can say more generally, not even thinking about binary numbers, not even thinking about Hamming weights at all. Let's remove those labels. We can say that n choose k for k equals 0 to n, partitions 2 to the n. Well, there you go, folks. That's what this was all leading up to, isn't it? We've got our little chunk of mathematical insight here. We boiled it down to the simplest truth. N choose k for k equals 0 to n. Partitions 2 to the n. So for k equals 0 to n. So n equals 3. Here we're saying d instead of k, but it's the same thing. You know, d equals 0 to 3, 0, 1, 2, 3. One, 3, 3, 1. Those numbers partition 2 to the 3, which is 8. So that is to say 3 choose 0 is 1, 3 choose 1 is 3, 3 choose 2 is 3, and 3 choose 3 is 1. All those numbers partition 2 to the 3, which is 8. So really drill that in. Really drill that in. Because this is a nice, complete little way of breaking up all those possibilities. You know? And that's really nifty. And that's where we're going to leave things today. We're just going to put this down today. You have to know when to put things down. Okay? So thank you very much for watching. And, you know, don't forget to subscribe to Josiah Genius. We're going to be having more content like this eventually. And yeah, we're going to move on to bigger and better things. But I'm glad we got to lay down this groundwork here, because this is going to be really important. You know, combinatorics, discrete math, you know, combinations. We haven't even gotten into permutations. Oh, goodness, you know. But soon. Or not, you know. Life has a way of finding its own pace. You know, so thanks a lot, guys. And you know what, just for you, we're going to draw a smiley face down there. Okay?